Okay, hello everyone. My name is Andrew. I'm going to be talking about advanced cryptography for communities. And once these slides load, So if you were at ZK Summit yesterday, you may have noticed that inside your badge, you had a little NFC card over here. And these NFC cards were issued by us. They each come with their corresponding digital signature public key. And so every single attendee gets a card with the public key, and every single talk also has its own card with the public key. And whenever you go ahead and tap a card, then you're going to get a signature from that public key. And what we've done is, on the side, we've built Merkle trees for a lot of interesting sets about people and talks at the event. And so, for example, we would have a speaker's Merkle tree, and this consists of all the speakers and their corresponding public keys. And so you can make useful proofs about, hey, maybe I've met a certain number of those speakers and I've tapped their cards. Now, going ahead, what is the point of this? We have all these NFC cards. You can go around the event tapping other people's cards. Like, why do we care? The first step is we need to understand why we're talking about digital signatures in the first place. Because digital signatures are really the core of this experience. Digital signatures, first off, are portable. An ECDSA signature is roughly around 64 bytes, depends on the encoding format you use. But it allows you to verify that a certain interaction, in this case in real life, was actually authentic, and it actually happened. The second thing is that they're context-free. And so compared to something like NFTs or something that maybe requires an API, digital signatures give universal verifiability. I don't need access to any API. I don't need any proprietary platform. If my device is able to verify a digital signature, which pretty much every single device is, then I can work with signatures. I can generate signatures, and I can take any signature that you give me, and I can verify that it's correct. And the final step here is that digital signatures are composable. So I think of signatures as the base layer for everything else that can be built on top in terms of advanced cryptography. So we want to start with signatures. That's what this whole project is about. These NFC cards are meant to have a sort of interesting set of signatures that were provided to every single person in this room, and then other people can come and build applications on top of it. So if there's anything I want you to remember, it's this. Digital signatures are the ideal base layer for advanced cryptography. Now, any of you in this room next year can decide, hey, at ZK Summit 12, we want to build our own application. We want to use event data. We want to know who people talked to. We want to know who people met. We want to know what talks people attended to. And we also wanted to know what they did at ZK Summit 11. Well, you can easily do it just from looking at the signatures that we've provided. So anyone can go into this app, they can export these signatures, and some other developer can build a totally different app that has absolutely nothing to do with ZK Summit 11 app and nothing to do with Cursive. And you can use these signatures out of the box. So there's nothing proprietary about this. Now, what can we actually build with this? So what does the app actually look like, and what sorts of cool cryptography experiments were we able to run? Well, first off, I'll walk you through the app. So if you ever tap someone's card, you'll see this screen. This is your home screen, and it kind of lists out every single thing that you've done at the event. So right over here, this means that I've tapped Andrew, and so we allowed any tap to do contact sharing as well. So when I go ahead and let's say I walk up to Ayush and I want to tap Ayush, well, I'm going to be able to see any of the contact information that he has agreed to share with anyone who taps him. In addition, I can go to any talk room, and I can tap in a card in front of the room, and I can prove that I've attended this talk. Now, with all these attestations, what can we actually build? First step is proofs. You can prove that you did certain things at ZK Summit 11. This is an example of what a proof looks like. So on the left, you can first collect a bunch of signatures. In this case, the proof that you generate is tapping into 5 talks. You want to prove to someone that you actually attended 5 talks at ZK Summit. What you would do is you would go to this room, you would tap in the 5 cards, you would collect these signatures, and then you're able to generate this proof. And after you generate this proof, you get a public link online that anyone can look at, and anyone can say, oh, this proof was actually valid, this person actually did attend those talks. And for right now, these proofs are hosted on our website, but you can easily copy the proof and host it anywhere you want. Now, here's where the fun stuff begins. Let's say that I walk up to Ayush and I want to see what we have in common. I've just met Ayush and I want to decide if I want to be his friend. Now, one way I can base this interaction off of is what sorts of talks he's been to and what sorts of people he's met at ZK Summit. And I can use that to determine if I like him or not. But I don't want to just send him every single thing and ask him, hey, like, what have you actually done? What talks have you been to? He might lie, I might lie. Also, I want to keep what I've done private. And so that motivates private set intersection. And this interaction looks a little bit like this. So I've collected a bunch of signatures, Ayush has collected a bunch of signatures. We walk up to each other at ZK Summit, and we both decide, hey, we want to discover what contacts and what talks we have in common. So keep in mind, this is an interactive protocol. So this uses two-party computation and fully homomorphic encryption. And because it's interactive, we sort of have to do it at roughly the same time. We don't have to press the button at the exact same time, but Ayush is going to have that same button, and we're both going to press the word discover. We're both going to say we want to discover our shared interests. Afterwards, it will run this computation, and then finally, we'll be able to see, oh, hey, like, we both know Sora, we both know Sachin, I like Sora, I like Sachin, so I probably like Ayush. Now, what's actually happening under the hood is I'm taking all my signatures that I have, I'm encoding my signatures as a bit vector of ones and zeros. Remember how I said that there are maybe 500 different public keys for attendees and talks at ZK Summit? Each one of those public keys corresponds to an index, and I'm encoding my signatures using those indices. Then I perform encryption alongside Ayush. We perform a two-party computation to encrypt our corresponding bit vectors. And then afterwards, in this encrypted land, we perform the index-wise product of these bit vectors. So we'll multiply these bit vectors, and then we'll get a resulting bit vector that says, oh, hey, at this index, we both have a 1, and so that's how I know that we both met Sora. Now, if you think about this a little more, I'll save this for homework, but you can think about this protocol. You might come up with some ways that someone could exploit this or possible attacks, but hint, hint, Enrico is going to give a talk later on about how to nullify some of these attacks. Third thing, also very exciting, is folding schemes. Now, to motivate this, one thing we wanted to do was have every single attendee be able to generate a final big proof of everything they've done at the event. So similar to how Spotify Wrapped takes every song you've listened to, all of your artists, all your data throughout a year, and it turns it into one big wrapped UI that you can look at, that people screenshot and just post on Instagram. We wanted to make a ZK proof for that. And for this, we wanted to use folding schemes. The advantage of folding schemes is that we can build this proof up incrementally. We don't have to have all the signatures at once and generate one entire proof of everything you've done at the event. But instead, we wanted to be able to fold in every single signature as you get it. And this allows us to experiment with the new technology, folding schemes of Nova, but also hopefully see if this is fun for the future. This is what this looks like. At the end of your event, you get this little folding-like UI that says, oh, this is how many attendees you've connected with, how many talks you've been to, how many speakers you've met, and you get to see all this, you get to review all of it, but then you get to generate this final proof. And this final proof basically takes in all the signatures that you haven't folded yet, and it folds the remaining ones in. And it allows you to publish this little wrapped proof at the end of the day. And this wrapped proof is something that you can post on Twitter, you can post online, and anyone can go visit this URL and say, oh, hey, like this is Andrew. He met 6 people at ZK Summit, but he also didn't go to any speakers. And you can verify this proof yourself again. Now, in regards to folding schemes were implemented by Jack's team, Mach 34. So he's going to give a little talk about it, but I'll hint at this a little more. He'll talk about this a little more, but folding actually takes a bit of time to run, and so folding every signature in, it would be difficult if we wanted to do it right when someone got it, because it would be blocking their entire UI experience. And so there's a ton of work done by Jack and Ian to actually make this work inside web workers. And so actually what's happening when you collect a signature by tapping a card, this is all happening in the background. These signatures are all being folded in whatever you're doing. Okay, bonus shout out here is email NFTs. Now this wasn't done at this event, but this was an activation we did with Ayush and ZK Email at ETH Denver. And so the idea here is that, okay, you have all these signatures. Because they're so composable, it's extremely easy to build any type of experience on top, including any Web3 experience. So if you care about Web3, if you care about NFTs, then email NFTs is a great prototype of how this might work. So we had a similar setup where you would go around and tap cards around the venue at ETH Denver, and when you tap a card, you got a signature. Now, Ayush and Sora helped us integrate this setup where you could go present the signature, or present a proof of this signature inside a contract. And when you sent this proof to a contract, then you would automatically get an email NFT. So everyone who signed up for the app had an email associated with them, and this contract would basically send them an email NFT, and you can ask Ayush more about how this works under the hood. Now, final thing I want to mention here is that a lot of this advanced cryptography is actually quite practical. It just requires a little bit of engineering work to make it happen. So ZK proofs, these proofs of signatures take around 1.5 seconds per signature. What we're doing there is an ECDSA verification and a Merkle proof. Running the PSI takes around 5 seconds. It's actually quite fast. It's quite fast compared to a lot of ZK proofs we want to make. But it requires both participants to be online. So it's interactive, and that's a limitation. Finally, folding takes around 3 to 5 seconds, depends on your device a lot. Jack will talk more about this, but we use web workers to make this happen automatically in the background, and so that's not a big limitation. And finally, I think the cool part about having this all be under the framework of signatures is that none of these teams technically needed our permission to build this. We just provided the signatures. We provided the front end for a way for people to actually go around and collect signatures. But Enrico could have decided, hey, like John Majai and Enrico could have been like, oh, like I want to build some FHE experience, right? I want to use signatures, and I want to say like, oh, like what's the private intersection for ZK12, right? And we could just have these NFC cards. We could give them out. We can give out signatures. But then people could export their signatures. You could just take them from local storage, or we could have some export functionality, and they could build a separate app, and anyone would be able to use it. And so, finally, I work at Cursive. We are a cryptography and design lab building applications of signed data and just working on advanced cryptography in general. If any of you want to collaborate on any of these types of experiences, build anything involving digital signatures, we're always happy to chat. Finally, shout out to PSE for funding this work. And here's our telegrams. This is my telegram. This is Cursive Telegram. If you're interested, you can join and chat.
When you were talking about the private set intersection, are you talking about like using beam filters, or is it more simple than that? When you were talking about like the big vectors and stuff, is it beam filters? Or?
Well, for us, the solution we actually implemented is each user just takes their list of signatures and encodes that as a bit vector.
Oh, okay. It's just a list. I got it.
Yes, yes. And so you might be thinking about ways where that can go wrong, or why that isn't a great solution.
Yeah, I'm just curious.
Well, Enrico's going to tell you why it's not a great solution.
Okay.